Hi there, Mr. Sutton here, bringing you the Pre-Cal Honors Chapter 3 Quiz 2 Extra Practice Solutions on Graphs and Inequalities of Rational Functions. On this problem, we need to find the intercepts, asymptotes, and holes of this function and then graph it. Before we can do that, though, we're going to need to factor it. So it looks like in my numerator, I can take a 3 out of there, giving me x minus 1 left over inside. In the denominator, I need numbers that multiply to negative 4 and add up to 3. So negative 1 and positive 4 would do the job there. X minus 1, x plus 4. And we see that the x minus 1s are going to cancel, leaving us with 3 over x plus 4 for the simplified version of this. Now that we've got that simplified, let's go ahead and find a few things, starting with the x-intercepts. These are going to be x values that make the numerator, the simplified numerator, 0. The problem is the simplified numerator just has this constant 3, which you can write equals 0, but it's not true. It does not equal 0. It never will equal 0, so there's no x-intercepts. For y-intercepts, we have to plug 0 into the original equation here. When we do that, everything zeroes out except for a negative 3 and a negative 4. So 3/4 then, if we reduce that, is going to be our y-intercept. For the vertical asymptotes, those are x values that zero out the simplified denominator, make the simplified function undefined. So if x plus 4 then equals 0, we have a vertical asymptote at x equals negative 4. Holes are going to happen wherever we have factors that get canceled out, and the x values that make those 0 are going to give us a hole. Those are values that would have made the original undefined, but not the simplified. So they're not as bad as asymptotes. So we can say x minus 1 equals 0 for the hole, and then x equals positive 1 is the x value where the hole happens. There's a y value too, but we have to graph the function before we can see where it is, or you have to plug 1 back into the simplified function. Either way. All right, so now we have to talk about horizontal asymptotes. Now looking at the relative degrees of the function, the original function, we see that we have a first versus a second degree numerator versus denominator kind of lineup here. This is a bottom-heavy function, higher degree on the bottom, so the horizontal asymptote is automatically y equals 0. All right, at this point, let's graph out what we've got. We may need to get some more points depending on how much information we have, but we have enough to at least start the process. We'll start with the y-intercept of 3/4, so that's going to be right about here. And the vertical asymptote at negative 4, vertical line at negative 4. The hole will hold off on. The horizontal asymptote at y equals 0, we can just draw that a little more dashed on the x-axis. And we see we're going to need some additional points. We only have 1 point, and it's on the right side of the vertical asymptote. We need something on the left side as well to figure out whether we're going to be in the upper left or the lower left for that branch of the rational function. So I'm going to plug in a number over here, like negative 5 or negative 6. Let me go with negative 5, and I'll put that in the simplified function here. It's totally fine to do that as long as you're not plugging in the x value of the hole. So we've got 3 over negative 1, which is negative 3. So we have negative 5 comma negative 3 right here, giving us another point. At this point, I can go ahead and graph the two branches of this rational function. So I have a branch that's hugging these asymptotes and going through this point in the lower left. And then I have another branch hugging the asymptotes and going through this point in the upper right. The last thing I have to do is remember this hole here. I have to put a hole on the graph at x equals 1. So I just go over to x equals 1, wherever that is on the graph, stick an open dot there, and call it a day. For this problem, we want to find all the key features and then graph this rational function. We can't really, we could maybe factor this, but it's not going to help us simplify, so we'll just hold off on factoring until the first thing I'm finding here, which is the x-intercepts. So those are going to be x values that zero out the numerator. To figure out what zeroes out the numerator, I need to actually factor it. So things that multiply to negative 4 and add up to negative 3, that would be x plus 1 and x minus 4. So setting each of those equal to 0 and solving, I get x equals negative 1 and positive 4 for the x-intercepts. Next up, the y-intercepts. If I plug 0 into the original function, let's see what happens. So I end up with negative 4 over 0, which is just undefined. So there are no y-intercepts. For vertical asymptotes, those are things that zero out the denominator. If I set negative 3x equal to 0 and solve, I get x equals 0. So that's my vertical asymptote. There's no holes here because nothing canceled out, no common factors canceled out. Horizontal asymptotes, well, this is a top-heavy function, second versus first degree. So that because it's top-heavy, there's no horizontal, but there are slant asymptotes, which I can find if I divide the numerator by the denominator. Now, since I just have a monomial down here, just a single term, I can just divide each of the numerator terms by this negative 3x. I don't have to use synthetic division here. So dividing everything by negative 3x, so we have x squared over negative 3x minus 3x over negative 3x minus 4 over negative 3x. We're just going to go ahead and simplify this, and that'll give us the slant asymptote. We have an x canceling in our first fraction, ending up with x over negative 3, which I can rewrite as negative 1/3 x. For the next one, basically I have negative 3 over negative 3, which is plus 1. That one wasn't so bad. And for this last one, we actually can just ignore it because slant asymptotes, those are happening as x gets very positive or very negative. So as x gets super big, this denominator gets infinitely large and basically pulls this whole fraction down to a value of 0. Super large denominator means super small fraction that we don't really have to pay attention to. All right, we've got some information. Let's put it on the graph and see if it's enough to actually draw everything. We may need some additional points, I don't know, but let's see what we've got so far. So for these x-intercepts, we have negative 1, that's going to be right here. Positive 4 is over here. We had a vertical asymptote at x equals 0, so there it is. And then we had a slant asymptote at negative 1/3 x plus 1. So there's a y-intercept of 1 right there. And the slope of that slant asymptote is down 1 over 3, down 1 over 3. So draw a downward slanting line there. And it looks like we actually have enough information to draw the two branches. We've got points on either side of my vertical asymptote. So I'm going to draw a branch that hugs the asymptote and goes through the point on the left side and does the same thing with the point and the asymptotes on the right side, like so. There were no holes to worry about at the end of this problem, so this is as good as it gets. To graph and write the inequality here in interval notation, we have to first get the critical values, which for a polynomial such as this are going to be just the roots. So let's go ahead and see if we can factor this thing and find where this whole thing equals 0. So one thing I noticed here, there's no common factors, but this whole thing is in quadratic form. We've got an x to the 4th, an x squared, and a constant. So I can treat this kind of like a quadratic and just use x squared instead of x when I'm factoring this out. So two things that multiply to 36 and add up to negative 37, that would be negative 1 and negative 36. So I can split this up into x squared minus 1 and x squared minus 36. And then I can split this up even further using my plus minus shortcut. I can call this x plus 1, x minus 1. And the x squared minus 36, I can split up into x plus 6 and x minus 6. At this point, I just have to figure out what zeroes out each of these parentheses, and those will be my roots. So I've got negative 1, positive 1, and now dealing with my last two parentheses, negative 6 zeroes out that third one, followed by positive 6. At this point, I'm going to put all of this on a number line. And for the dots I'm going to use, since I have no equals in my inequality, these are all going to be open dots. So my furthest one to the left is negative 6, that's all the way over here, followed by negative 1, and positive 1, and then positive 6. Now I'm going to plug in a number from each of these intervals and see if this whole thing comes out positive or negative as a result. So I'll choose negative 7, that's to the left of negative 6. So plugging in negative 7 plus 1 is negative, minus 1 is also negative, negative 7 plus 6 is negative, and minus 6 also negative. 4 negatives, an even number of negatives gives me a positive overall result, and I move on to the next interval. So I'll use negative 5 for this one, Anything between -6 and -1 would work, though. -5 plus 1 minus 1, those are both going to be negatives. Plus 6 is going to be a positive, and then -5 minus 6 will be a negative. That's 3 negatives. Odd number of negatives, whole result is negative. Next, between -1 and 1, I'm going to use 0. That's a pretty easy one. So we'll have plus 1, minus 1. That's a 1 negative and 1 positive so far. This next one is positive, followed by a negative. So that's 2 negatives giving me a positive. Plugging in something between 1 and 6, let me use 2. So 2 plus 1 is positive, minus 1 is positive, plus 6 is positive. The only negative is 2 minus 6. 1 negative gives me a negative result. Finally, something bigger than 6, like 7. 7 plus 1, minus 1, plus 6, minus 6. Those are all coming out positive, so this whole thing is positive. Next, looking at my inequality to see which intervals I really want, I notice that we have less than 0 as the inequality, so that means I want all the negative intervals. So that'll be this second and fourth interval. And now to write those in interval notation, I've got one going from -6, comma, -1. Those will be parentheses on both numbers because I have open dots. And then I'll have a union, 1, comma, +6, also with parentheses. For this inequality, to get the solution, I'm going to go ahead and find the critical values and do sign analysis on those. Critical values are going to include both roots and discontinuities, basically anything that zeroes out either the numerator or denominator. To figure out what those x values are, I'm going to have to factor this first. So taking a look at my numerator, I need two numbers that multiply to 27 and add up to -12. So we got 1 and 27, that doesn't work. 3 and 9 would work if they were both negative. So I'll do x minus 3 and x minus 9. Downstairs here, I have a common factor of 4 that I can take out. And that's going to leave me with an x plus 2 left inside. Next, I'm going to write down my discontinuities first. I always do that just to make sure I don't miss any. So we'll have -2, the x value -2 zeroes out that denominator. And now for the roots or zeros, that's what zeroes out only the numerator. So going from one parentheses to another, we've got +3 and +9. Let me go ahead and put those on a number line now. So the furthest one to the left is this -2. Since that is a discontinuity, that's going to automatically be an open dot on -2. The roots could be closed dots if my inequality had an equals, but it doesn't. No equals here. So these roots will also give me open dots. They're not part of my solution. They're really just boundary markers. So we've got 3 and an open dot on 9. Now I'm going to choose a number from each interval and do some sign analysis. So from -2 to the left here, -3 is a good number to use in there. So that's going to give me -3 minus 3 is negative, minus 9 is negative, -3 plus 2 is also negative. 3 negatives, odd number of negatives, gives me a negative. And then between -2 and 3, 0 sounds like a good number to use. So -3 is negative, minus 9 is negative, plus 2 gives me a positive. So that's 2 negatives giving me a positive result. Between 3 and 9, let me use 4. 4 minus 3 is positive, minus 9 is negative, plus 2 is positive. We just have one negative there, so that's a negative result. And finally, after 9, let me use 10. 10 minus 3, minus 9, and plus 2, all of that coming out positive. So positive result. Next, looking at my inequality, we have less than 0 as my inequality. So that means I want all the negative intervals. That's this region right here on the far left, and also this third interval. Writing down the solution for all of those, my first interval is going to go from -infinity to -2. Those are both going to be parentheses, because I have infinity and an open dot. And then I need a union to get this other group here from 3, 9. Also open dot, so also parentheses.